This bit on equivalent conditions for non-singular matrices is one of the most important things that we'll talk about in this section. And let's just look at this. It says these are equivalent conditions. If A is an n by n matrix, then all these things are equivalent. It means for that matrix either all of these are true or all of them are false. So let's see, A is invertible. AX equals B has a unique solution for every correct size column matrix B. AX equals the zero vector only has the trivial solution. A is row equivalent to the identity matrix. A can be written as a product of elementary matrices. We kind of skipped over that part, so that one is not quite as important for us here. But 6 here, the determinant of A is non-zero. Now, I want to talk through a few of these things because I don't want you to just sit here and memorize these things. I want you to understand what's going on. So let's look at this. A is invertible. And if A is invertible, then A is row equivalent to the identity matrix. Well, that makes good sense because the thing we learned for finding the inverse was to put A here, and then put the identity over here, and then row reduce. And remember, if this row reduced to the identity, then this over here gave us A inverse. So those two kind of make good sense because that's how we find the inverse. I also want to look at these two things here, part numbers 2 and 3. So suppose A is invertible. For number 2 here, it says AX equals B has a unique solution. Well, let's say we wanted to solve AX equals B. We would probably write that as an augmented matrix. We put A over here, augment line, and then B. And we'd row reduce it. And if A is row equivalent to the identity, we get the identity matrix over here, and we get whatever numbers over here. And if it row reduces to the identity, that means there are no free variables. And it also means that every one of the lines here has a leading 1 on it. So this is going to be 1 and then a bunch of zeros. And so on. So when we read off of there, we're going to get just a single solution. And if this up here had been 0 instead of, if this had been 0 instead of B, if these were all zeros, then what we would get out of this would be that the first variable is 0, the second is 0, and so on. That's the trivial solution. So anyway, these are important equivalences here. And as we learn new concepts during the semester about things like linear independence, things about rank, things about eigenvalues, when we learn those things, we'll get additional lines that we can put on here. So let's look at some examples. Rather than write out my own examples, I decided to just pull a few things out of the homework for this stuff. And I want to go over those. So let's look at this 201 example. It says the determinant of a matrix. And these things, find A, the determinant of A, the determinant of B, AB, and the determinant of AB. And then verify that, this is a mouthful to read, verify that the determinant of A times the determinant of B is equal to the determinant of the product AB. So let's do that with octave. Let's see. So if I put in A is 201, 1, negative 1, 2, and 3, 1, 0, and B is 2, negative 1, 4, 0, 1, 0, 1, 3, and 3, negative 2, 1. We've got that. So the determinant of A is 0. So I typed that in right. 2, 1, 3. Yeah, they meant for that to happen. So determinant of A is 0. Determinant of B is negative 7. And so if we take A times B, we get this matrix, and its determinant, they want us to verify that it's equal to the determinant of A times the determinant of B. So this should be 0. Sure enough, it is. All right, what's the next example? It says classifying matrices as singular or non-singular. Use the determinant to decide whether each matrix is singular or non-singular. All right, so on these, all they're really asking us to do is to determine if it's singular or non-singular by taking its determinant. So let's just do 20. So 20, I'm going to take the determinant. I could do this with octave, but I'm going to do it by hand. When I take this determinant, let's see, I get 3 numbers there. What are those? 24 plus 0 plus 0. That's nice. When I do the back diagonals, I get let's see, 6 times 4 is 24 times 2 is 48. Then I get minus a -3, then minus 0. So what do I get there? 24 minus 48. You know, it doesn't really matter what the actual number is. That's not 0. Therefore, the matrix is non-singular. It's invertible. They're using singular versus non-singular here. The thing to remember is singular and invertible mean the opposite. Non-singular and invertible are the same. The way I tend to remember that is people call like a black hole singularity. That's a place where the mass over space becomes essentially the amount of space. The density goes to infinity because the amount of space that the mass is in shrinks to 0. So, you know, 0 means singular, and non-zero means non-singular. All right, let's look at this next one. It says, use the determinant of the coefficient matrix to determine whether the system of linear equations has a unique solution. All right, let's do number 34. And let's use octave for this one. Really, what they're wanting us to do here is just take the determinant of the coefficient matrix. So I'm going to call it C. Coefficient matrix on 34 is going to be 1, 1, -1. Then 2, -1, 1. And then 3, -2, 2. Let's take the determinant of this thing. This is an interesting thing. The determinant of this, it gives us this ugly looking number. But if you look at what that is, it's 0. It says 8.32 times 10 to the -17. Well, what's going on there is the matrix here is, it has a determinant of 0. The computer is doing this with, you know, with computer arithmetic, and it's getting some round-off error. So this thing is it's a singular matrix, and so the system does not have a unique solution. Let's row reduce this and see what we get. Notice row reducing it, we get something that's not the identity matrix, and that makes good sense. Now, what happens if we try to take the inverse of this? Take the inverse of C. Notice it gives us an error. Let me slide this over so we can read the whole thing. Sliding the wrong thing here. It says, warning, matrix is singular to machine precision. And then I don't know what the rest of that means. But what that means is the matrix is singular, but when the computer does all of this stuff, it gets some round-off error. And when it tries to compute the inverse,